Scientific notation. Scientific notation is a way of writing very large or very small numbers. Or, that's an R. And we write these very large or very small numbers in a way that's easy to read. And this is going to make more sense if we come back to it afterwards, but I'll write it in. We write it as, so here's a very, very large number, and it's got lots of zeros in it. And we're going to write it as a number that's between 1 and 10. That is, it's only got one digit in front of the decimal point. So to get this number to be like that, it would be 4.5. Now, obviously, 4.5 is not 4,500,000. So there's other stuff we've got to do, but this is our first step, writing our number as a number between 1 and up to 10. So we write it as a number between 1 inclusive and 10, and I'll talk about this in a minute. And we multiply that by a power of 10. Sorry, power. Now when I say 1 inclusive and 10, what that means is, since I'm allowed one number in front of the decimal point, I could have 1.000, the smallest number I could have is exactly 1. So I could have 1. This includes 1, that's what inclusive means. But for having one number in front of the decimal point, I can't have 10, but I could have 9.999, saying that I can go up to but not including 10. And the way we write that instruction mathematically is I'm going to say that my number, which we'll call A, my number is greater than or equal to 1. So 1 is less than or equal to A. And my number is less than 10, but not equal to. So we've got notation to describe what I just put there. It's basically a number with one digit before the decimal point. Sorry about my writing went dodgy there, sorry. And our rule, written algebraically, is that we write it in the form A, this number, times a power of 10, where the power m is an integer. Oh my goodness, integer. I'm sorry, this is not a good day to be making videos. This is our big important formula here. This is also very important. So, trying to summon some brains here. Sorry about the vacuum cleaner noise outside. For large numbers, that is 38 million years. That's 38, 1, 2, 3, 4, 5, 6. It can be difficult to glance at a number and see if it's 38 million or 3.8 million or 380 million because we have to go carefully counting zeros. So scientific notation makes it much clearer what the order of magnitude, basically the number of tens, is, or the number of zeros that we've got tacked on the end. So the only way to write 3 and 8 there as a number between 1 and 10 is 3.8. Now obviously this number is not 3.8, nor is it 380 or 3,800. If you kept multiplying 3.8 by 10 until you got back to this number, you would be multiplying it by 10 to the, here's my decimal point at the moment, 3.8, 1, 2, 3, 4, 5, 6, 7. You'd be multiplying it by 10 7 times to get it back to here. So 3.8 times 10 to the 7 is equal to 38 million, and they told us that was years, so I'd better say that's years. So it's quite logical. Very small numbers, now large numbers use positive powers of 10. Small numbers use negative powers of 10. And we'll have a look at why that is. 417 nanoseconds, a very small amount of time. That's 0. If I wrote that in seconds, that is this very small number. Again, it's not easy to glance at it and see, is it 417 nanoseconds or 41.7 nanoseconds? I don't know. It's hard to read quickly. And being out by a factor of 10 in scientific calculations is pretty drastic. So, scientific notation says, rewrite as a number between 1 and 10. So all these zeros aren't very helpful. You can't have 0.4. That's not between 1 and 10. You've got 4.17. That's between 1 and 10. Tick, good. Now, obviously, this number is much smaller than 4.17. So it doesn't feel like we're multiplying by 10 each time. Because actually, we kind of want to be dividing by 10 each time. And remember, dividing by 10 is the same as 10 with a negative 1 index. So this is why we end up having a negative power, because 10 to the negative 1 can be thought of as divide by 10. If I've got 4.17 and I wanted to get it back to being this really small number, how many times would I have to divide by 10 or multiply by 1/10 to get back to it? 1, 2, 3, 4, 5, 6, 7. So this is times 10 to the negative 7. Now you can think about this as you're moving the decimal point 7 spots to the right to get a bigger number. You're moving the decimal point 7 spots to the left to get a smaller number. It's not really very accurate to think about it like that. Actually, you're multiplying by 1/10 or dividing by 10 7 times. Really quickly then, write in scientific notation 4,500,000. Write it as a number between 1 and 10 times the power of 10. If the decimal point's here, we'd have to do 1, 2, 3, 4, 5, 6 times 10 to the 6. This one, 4. Now we always have to have a decimal point. So even though there's no 0 after it, 4.0 times 10. If the decimal point is here, 1, 2, 3, 4, 5, 10 to the negative 5. Totally forgot to write the questions in here. A question might ask you to take it out of out of scientific notation and into either what they call decimal form or standard notation. Just get it back to a decimal or a whole number, basically. So you write your digits that you have. Now you can draw this in if you want. The decimal point was here. 10 to the 5 means we're multiplying by 10 5 times. 1, 2, 3, 4, 5. My decimal point ends up there, and when you're jumping over space, it means you're putting in some zeros. It's not very mathematically correct to sit here jumping the decimal points. you're really asking yourself, how many times am I multiplying this by 10 and getting your answer? So I would expect you to rewrite this at very least, without all the little jumps on it. 4.71 times 10 to the negative 5. Obviously, you've got your 4, 7, and 1. Your decimal point was here. You've moved it to the left because you are dividing by 10 or multiplying by 1/10. If you want to draw in the little jumps, you can. 1, 2, 3, 4, 5. Decimal point goes there. Don't forget there would be a 0 before the decimal point. Zeros under any jump you'd made. 0.0000471. Now, yes, you can work this out on your calculator as well. Type it in, get the answer. It's a good idea to check. But you are being aware of mathematically why we're doing this. We don't actually pick up decimal points and jump them. It's just that it looks like that happens when we multiply or divide by 10. Some extension concepts if you're interested. Sometimes they give us something that isn't in scientific notation but is sort of. So that 38 is not between 1 and 10, so it's not in scientific notation. But we could change 38 itself into scientific notation. That's 3 times 10, 3.8, sorry. 3.8 times 10 to the 1. But then, that's 38, and I need to times by 10 to the 3. Index laws say that 10 to the 1 times 10 to the 3 is 10 to the 4. So this is 3.8 times 10 to the 4. Same thing here. The only way to get this to be between 1 and 10 is to have it as 8.0 times 10 to the negative 2, 1, 2, times 10 to the negative 3. So gathering those with index laws, negative 2 plus negative 3, says I've got 8.0 times 10 to the negative 5. Now it looks a bit pointless, but it can be quite useful when we're adding or subtracting in scientific notation. So we'll come back to this little concept. Multiplying numbers in scientific notation, 9 times 10 to the 3 times 5 times 10 squared. Multiplication can be done in any order, regardless of the brackets. So you multiply sort of the coefficients, the A in our scientific notation, and then you multiply the powers of 10. So I've got 9 times 5 times 10 cubed times 10 squared. So I've got 45 times 10 to the 5. Now that's not in scientific notation yet. We've ended up with something like this. So that's kind of useful that we just learned how to do this, because that's 4.5 times 10 to the 1 times 10 to the 5, 4.5 times 10 to the 6. Now yes, you can grab your calculator, but this shows that you understand scientific notation, and it's often quicker, especially if you're kind of good and you can go from here to here quite quickly. It's often quicker to do this than it is to grab your calculator. If you're adding and subtracting in scientific notation, you want your powers of 10 to be the same. And then you can just add or subtract the coefficients of the powers of 10. That is the A number that's between 1 and 10, which is really quite useful. So you'll have to change one of these, change the big one. So I've got 2 times 10 to the 3 plus, now I'm going to basically take this down to 10 to the 3, which means that's 3.6 times 10 times 10 to the 3. This one's staying the same. This is now 3.6 times 10, 36 times 10 to the 3. Now that I've got it as both powers of 10 to the 3, or both times 10 to the 3, I can effectively factorize 10 to the 3 is a common factor. So I'm multiplying by 10 to the 3, and in brackets I've got 2 plus 36 times 10 to the 3. That means I've got 38 times 10 to the 3, not in scientific notation yet, so this will be 3.8 times 10 to the 4. So some interesting little things that you can do with scientific notation.